Hello everyone, my name is András and I am going to tell you about our first steps in the machine understanding of radiologic reports. Even in our home city of Szeged, Hungary, there are thousands of new radiologic reports generated each year only from the spinal region. So there is a lot of information in that. And yes, image information that is made during the examinations is very valuable and contains a lot more information than simple text, but the expertise and the experience of the radiologists are only located in the reports themselves, because this is the output of their work. And this holds a number of potential benefits. It could be used for quality assurance of the report composition itself, because it could provide real-time support for a radiologist. It could contribute to quick comprehension of radiologic reports for radiologists and also for patients, because patients usually struggle with understanding the reports. They could make it easier to compare the reports to previous ones and ascertain the benefits of treatments, and they could provide valuable statistics for hospitals and other institutions. And of course, this could be used as training data for other machine learning techniques. They require a lot of training data, which is very costly to make. It would require radiologists to work for months or even for years to compose training data that would be adequate for an image-based method to work properly. But this information is already available in the reports, but it's in an unstructured manner. So if we could understand that, we could potentially use it for training and make something great out of it. The overview of our process can be seen in this image. We will talk about the individual parts, but let us first follow this through. 487 spinal MRI reports that were written in the Hungarian language were manually annotated by radiologists. And these annotations were used for training data for a classifier that also aimed to find these entities. This classifier is based on bidirectional long-short-term memory and conditional random fields. Other semantic information is also extracted from the text via linguistic analysis, and this is used for determining the connections between the entities and considering the negations. So 487 Hungarian spinal MRI reports were manually annotated by a radiologist, and this was done along specific annotation guidelines. The radiologist annotated 3 different types of entities. Anatomic locations, these are of course the parts of the body like discs and vertebrae and bigger parts of the spine and things like that. There are disorders. These are the things that the radiologist sees on the image. These can be some pathological disorders or even some proper state, like the disc is being intact, for example. There are also properties which tell us more about, the properties of the disorders themselves, usually. There is a 3 millimeter protrusion somewhere. The classification itself is performed by BioSTM CRF classifier, which uses character embeddings and various other linguistic information like part of speech tags, part of sentence, and lemmas. These are extracted by the Magyar Lánc Hungarian Linguistic Analyzer tool. The BiLSTM layer's output was passed through a densely connected feed-forward layer, on top of which there is the CRF layer, which performs the actual final sequence tagging. We did not aim to only classify tokens as locations, disorders, or properties. We wanted the whole terms. Thus, we performed an inside-outside beginning tagging on these, and these went into the training data as well. This table showcases the results of our classification experiments. It is easy to see that locations provided the best results. Anatomic locations are rather simple, and they are just, well, simple parts of the body, and there are not a lot of variance in them, at least in the spinal region. Disorders are a little bit harder, but they are usually also well defined. They can have various names like Hungarian names and Latin names, and there is a lot of overlap between them, but these are also rather simple. Properties are much harder because they are much less well defined. They can have a great amount of numbers in them, and well, almost anything can constitute a property. Our process achieved about 90% precision and recall values. Classification is great and it produces a lot of colorful words in the text, but there is a lot more semantic information that could also be extracted. This was mostly achieved also via linguistic analysis. This here is a Hungarian example. You can see English examples also throughout the slides and the paper, but those English examples were specifically constructed for the presentation and for the easier understanding. Our process in the current state does not support the English language, but there are, of course, plans to also involve English radiologic reports. These constituents are then used in combination with a set of rules that we created. This is a very comprehensive set of rules about the connection of different entities. Here you can see some really simple examples. Like in the first constituent, there is only one location and one disorder, and our rules say that they should be connected. Finally, a structured compact representation is constructed from the report, which is easy to comprehend. This is in a tree structure in which the locations are the roots and the leaves are the properties, if there are any. So, to summarize our work, the reports contain valuable information that could be extracted and used for other purposes, like for example, the training of machine learning experiments, also for image information extraction, and our work consisted of manually annotating 487 radiologic reports and then training a BiLSTM CRF classifier to classify these along locations, disorders, and properties. Then connections and negations are also considered, and these are extracted via constituent parsing and other rule-based methods. And we constructed an easy-to-comprehend tree-like representation. In the future, these methods will be perfected and used for various purposes, like the ones that were mentioned at the motivation. This is mainly the groundwork for other larger experiments, for example, generating training data for image classifiers and like providing a better automatic understanding, not just for Hello, everyone. So now, hopefully, you see me, you hear me. Great. So, do you have any questions? We don't have much time right now, but I can answer some quick questions.
Any question, please?
Okay.
András, I saw that in your presentation that you are not working with any other languages. Are you planning to introduce new alternatives in your proposal for providing this support?
Well, yeah, we are planning to involve the English language also. We are currently doing some experiments regarding to that. Actually, right now, there's a radiologist who does the annotation for us for English reports also.
Yes,
There's a question.
Ita was asking as well whether it would be quite difficult to develop the version for English.
Yeah. Well, it would be. There would be some difficulties in it, but I think we could cope with it because there are already very good English language support methods for linguistic analysis and nearly everything we do. Machine learning techniques mainly rely on data. So if we can get the data, which is resource intensive, yes. But if we can get the data, there is theoretically no real obstacle for English methods also.
And Javier is also asking whether there is any qualitative feedback from the ones that you report.
Well, that's a funny story that the radiologist who actually did the annotation for us, he also wrote some of the reports. They were anonymized, so we didn't know which ones he wrote, but he told us that he wrote some of them. So yes, we have some qualitative feedback from the authors themselves also, but otherwise there are also some other radiologists who we work with who don't work in the same city where we live, and they also did some testing for us. And well, our qualitative feedback right now says that we're well above 90% in every aspect, just like our machine learning evaluation said. So it looks great right now, but well, it still needs some testing.
Okay, thank you, András. We are finishing now.